All right, so here is another example of a triple integral rewriting the bounds. So we're going to go ahead and do this problem 31, and we're going to do 32 because it's a continuation of it. Over here in CalcPlot, we can go ahead and graph this. Right now, this is just the default surface that comes with CalcPlot. So I'm going to just delete that. And what we can do here is when we read this, it says that W is the region bounded by z equals 1 minus y squared. So let's go ahead and add z equals 1 minus y squared, which should be a parabolic cylinder. In other words, it's a parabola. Z equals 1 minus y squared. It has a z-intercept of 1. It's a parabola that opens down in the yz plane, but because this equation doesn't have any x in it, that means the parabola will be basically stretched infinitely far in the x direction. So that's exactly what we have here. Our parabola has a, if we were to view this sort of above the yz plane, not perfectly above it, but you can see that it does in fact have the properties that we anticipated. A z-intercept of 1, and it's a parabola that opens down, and it just stretches itself in the x direction. So now we can go ahead and add the second function here, which is y equals x squared. So like the previous one, this is also going to be a parabolic cylinder, but because it is solved for y, this means that it will extend forever in the z direction. So in the xy plane, it is a parabola that opens upward. So if we go ahead and type this in, y equals x squared, we should see, there we go. So I can turn off the first parabola, and we can see that in the xy plane, let's view it the usual way, like that. In the xy plane, we have that parabola that opens upward. Adding back in our other one, this extends in the z direction. So let's go back to our standard axes in 3 space, which looks something like this. So y to the right, x out of the page, let's say, and z directly upward. Now they give us another thing, another surface, and that is the plane z equals 0, so above the xy plane. So I'll go ahead and add that, z equals 0, that one's easy, so we get that. So with that, we should be able to now look at that, and we can take a minute here to just adjust some things. So I'm going to go ahead and just very quickly adjust some settings here to clip things. So we don't care about what's below the z equals 0 plane. So I'm going to just adjust the settings of these graphs to sort of section things off a little bit. All right, so here what we have, I went ahead and just clipped things down a little bit, adjusted the range for x, y, and z to really only capture the parts that we absolutely need. In particular, I went ahead and made the range for x, y, and z from -1 to 1, because that's really where this intersection happens, because we're interested in the region that's bounded by these 1, 2, 3 surfaces, which is sort of the interior of this, underneath of this surface. You can kind of think of this parabola here, this parabolic cylinder, you can think of this as the ceiling if we're thinking about in the z direction. This is the top surface in the z direction. The xy plane, z equals 0, this yellow plane, that would be the floor, and then this parabolic cylinder, y equals x squared, is sort of the walls that surround it. So what I can also do here, there's another tool that I can use where I can create a region that sort of sections this whole thing off. So I can show you what I'm going to do there. So now you can see that I have the controls listed over here, and I can toggle on or off these surfaces, and that's how I can adjust the settings. This is where I clipped it from x, y, and z from -1 to 1 for all of them. What my goal is to show you how we can actually describe the same region here in a more succinct way that's probably better suited for triple integrals and 3D region visualizations. So what I'm going to go ahead and do here is turn those all off for the time being, so we're back to a blank plot. I'll also reset my view by clicking the home button, at least on a Windows machine. Now if I go ahead and add to graph, I can select the region tool, all right, which we have here. You didn't see the menu because that wasn't captured, unfortunately, in the video here, I just noticed. But if you select this button down here, add to graph, one of them does say region. I don't know why that's not showing up. Anyway, in here, it shows us something that is useful later on, but right now I'm just going to close that. So that's this button right here. If I click that, it will collapse it. And this is really the region thing that we added. These bottom three things are what we had originally. That's the surface. But I'm going to leave those turned off and just focus on this region. So what we saw in 3D was that the top was the surface z equals 1 minus y squared. That was the top. The bottom was z equals 0, right here. And then the thing is, we want to know what the shadow is in the xy plane. So if I turn this off for a second and turn these three back on, we can go ahead and I'm going to set our view to above the xy plane, which I can accomplish on a Windows operating system with Control Home, and I can view this above the xy plane. Now notice we want the region that's bounded within the z equals 1 minus y squared parabola, which is this one right here. Y equals x squared is this, and then z equals 0. So you can see that if we smush this into the xy plane, really it's this parabola, y equals x squared, that sort of cuts everything off in the xy plane. So if we were to smush this region down, then the region within here is the region within this parabola. So what I'm going to go ahead and do here is go ahead and reset my view, delete those, and turn on this region here. So here, let's type in the y equals x squared. And that gives us something that's a little bit different than what we expected. Because really, for our region to match up, that's actually the bottom surface, and the top surface is where this parabola z equals 1 minus y squared hits the xy plane. And that parabola z equals 1 minus y squared hits the xy plane in two locations. It hits it back here, right? I can turn this on. So if we turn this on, you can see this parabola hits the xy plane over here, and it hits over here, and that's, you can figure this out by setting this equal to, set z equal to 0, and solve for y. So you get y equals plus or minus 1. So let's turn that off, and let's make positive 1 be the top surface. So now you can see that this exactly is the piece that fits within. If I add them all together, a little bit ugly here, but that does perfectly fit right in here. So if I take off the top, we still have that piece. I can take off the sides, we still have this piece, and even if I delete the bottom, we get that piece. So that is our three-dimensional solid region over which we are supposed to be integrating. So this region tool in CalcPlot 3D can really help you visualize things. Unfortunately, it has one major drawback, and that is it definitely thinks of things in a z-simple manner. So it wants you to describe your region with a solved for z for your top and your bottom. And then it projects down into the xy plane for your two-dimensional region, your shadow region. So we can't do triple integral, at least we can't set it up in such a way in an x or y simple manner. All right, so the next thing we're going to go ahead and do is work on getting the first integral here, which would be in the order dz first. So if we do that, this means if dz is going to come first, that means we want to think about what is, if you were to take a line, which I've created here in green, if you take a line and you can imagine moving this throughout your region. So let's go ahead and actually move this. So I created the line here, A, B, C, where A, B, and C are just parameters, so I can slide the values and change things. Along with, this line doesn't need to go on forever, so, but whatever. So I'm going to go ahead and move the x and y location. So you can think of this as stabbing down. It's going to eventually hit the xy plane at some point a, comma, b, comma, 0. So if I change the value of a, that's going to move the line. So let's make the x value smaller, and then the y value also smaller. So now that we're within our region here. And you can see that no matter where you move this line, if we just drag this around, slide it left and right, or up and down in the y direction, no matter where you move this, as long as it's in the region, notice that if you think of stacking things in the z direction, this parabolic surface right here, which I will really quickly just flash on the full thing, that surface right there is the top surface. And then down here, this is the xy plane, z equals 0. That is the bottom surface. So whenever you start a triple integral in a certain differential, so let's say dz comes first, imagine poking a rod, which is illustrated by this green line that I have parameterized on the side. Imagine poking your region with a line or a rod parallel to that differential's axis. So if we're going to do the order dz first, then poke it in the z direction. Then that will hopefully stab two surfaces, and only two surfaces, a top surface and a bottom surface. You want to just identify what the top and bottom surface is. Once you have it identified, that literally tells you what your bounds are for that first inside or innermost integral. So what I'm going to go ahead and do here is show you how we're going to build this triple integral. All right, so just rearrange my screen a little bit here so we can take a look at everything. So far we've identified what the top and bottom is. So right now for this part 1, we're going to go ahead and do the order, excuse me, I meant to say dz, dy dx. So what you do is, since we're doing dz first, this means we're going to let d be the projection maybe I'll call this d sub xy. Let d sub xy be the projection of our solid region W, our solid region, onto the xy plane. So with that being said, what we want to do now is identify this. dy dx. So that's ultimately what we're trying to set up. Now for this problem in the textbook here, if I quickly remind you all of what the textbook is, the textbook problem that we were doing was to calculate the volume of W. So for this, for volume, whenever you're doing volume, the function that you're going to be integrating here, this function is going to just be 1. So I'll write that out here. For volume, your function of 3 variables for a triple integral is just equal to 1. So in this case, we're going to have 1 as the integrand, and then we can take this and just slide a little bit closer. And furthermore, you don't even have to write the 1. You could just write dz, which is even more succinct. So let's go ahead and do that and then just collapse this even more. Now, do you actually need the set of parentheses here? Absolutely not. But the basic idea for a triple integral is really whatever your first differential is, your innermost differential, what you need to do is in that order, you need to figure out what's the bottom and top surface, which we've done. If we look at our graph over here, we just argued that the top surface here is the parabola, the parabolic cylinder z equals 1 minus y squared. So that's the top surface. So that means that's going to be our innermost, our top bound, I should say. And we can just ignore the outer 2 integrals. So I'm not going to write the parentheses here, but I'm trying to emphasize that really, whatever your first differential is, that dictates everything that's going on right here. And then this you can worry about after the fact. You figure out this by taking your 3-dimensional region here and then projecting it onto the xy plane. So again, if we'll do that in a second here. So our top surface is z equals 1 minus y squared. And our bottom surface, we argued, was the plane z equals 0. That's our bottom surface. So there we go. Now how do we figure out this d sub xy, the projection of our solid region W onto the xy plane? Well, we can take a look above the xy plane and we can see our line. We can still move it around in our region, but we're just viewing it now where the z-axis is coming directly out of the page or out of the screen. So here we can see that if we enable this parabola y equals x squared, that is exactly what that bounding curve is. So in the xy plane, our bottom surface is this parabola. Our top surface is where this cuts off, which is y equals 1. So this region in the xy plane is actually both vertically and horizontally simple. Now, because for this problem they said do the differential dy first, then dx, we want to interpret this region here as vertically simple. So if we go ahead and do that, effectively, I'm just going to, off to the side here, say that d sub xy, we can say that x is between what 2 constants? Well, this parabola here in the picture, if we go back and look at the picture here in the xy plane, or above the xy plane, it intersects here at x equals -1 and 1. Now, without a graph, how would you do this? Well, without a graph, let's backtrack for a minute here. What I would actually do is take, I'd go ahead and take the parabola z equals 1 minus y squared, see what it looks like when you intersect it with z equals 0. which gives us y equals plus or minus 1. So in the xy plane, we've got this line here, y equals 1, and y equals -1. Okay. And then we would also graph the equation y equals x squared. So then you want to know those two x values. Well, take this equation here, y equals 1, and set it equal to y equals x squared. You'll solve and get x equals plus or minus 1. There we are. So with that, we can say that this region here, d sub xy, x ranges from -1 to 1, y ranges from x squared to y equals 1. So then we can complete this triple integral by writing the integral from -1 to 1, the integral from x squared to 1, integral 0 to 1 minus y squared dz, dy, dx. And that is the order in that, dz first. All right, for the next bit, we're going to go ahead and do the triple integral in the order dx, dz, dy. Now for this order, we are going to imagine poking our solid region with a line or rod parallel to the x-axis. So that's what I have drawn here with this green line here. I can go ahead and, so the x-axis is coming out of the board now. So I can go ahead and slide my line in the y direction, so left and right from our perspective currently, and then I can also move it up and down or in the z direction. So no matter where I move this line, as long as it's in our region, it looks like it's stabbing, well, so the positive x-axis might be hard to see from the size of the video here, but the positive x-axis is coming out of the page, out of the board, out of the screen, whatever you want to say. So this half, so this green surface here, looks like it's the quote-unquote top surface in the x direction. And then this surface on the other side is the quote-unquote bottom surface. But here's the thing. These two surfaces are not actually different. Both of these surfaces are that parabola, y equals x squared. So it's the same surface. So when we're going to come over here and think about the ordering for x, for instance, what two surfaces does x live between? Well, right now it looks like we've got our same surface, y equals x squared, as both the bottom surface and the top surface. Okay? Which might seem a little confusing. Well, here's the thing. Whenever you write down an inequality like this, whatever you put down here and up here, it has to be solved for whatever this middle variable is. So we're not going to write something like x squared and x squared here, because how can x be simultaneously less than or equal to itself squared and greater than or equal to itself squared? The only way that's true is if x is 0 or 1. So that's not going to work. So always, 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 no matter what this is, whatever you want to put here, whatever surface's equation you want to put here, you have to put this surface's equation in the form of it's solved for this variable. So that prompts us to actually take this y equals x squared, solve it for x to get plus or minus the square root of y. So the negative root goes down here. The positive root goes up here. So this immediately tells us that our triple integral will be the double integral over, let's say, d sub y sub z, where this is the projection of our solid region onto the yz plane. The integral from negative root y to positive root y, our function is still 1, so we'll have 1 times dx, and then we'll have dz dy. So right now we've got our inner bounds figured out. And this was a little bit different than last time because this forced us to solve for the other variable. Last time we didn't need to do that because our surfaces were already solved for z, because we had the plane z equals 0 and the parabolic cylinder z equals 1 minus y squared. Okay. So now that we have that figured out, what we want to do here is project this region onto the yz plane. So if we look at the yz plane, this would be, let's see here. There we are, the yz plane. So if we look at the yz plane here, looks like we've got this, this kind of shape here. So what is this green surface here? Well, that green surface is the same, or excuse me, it's the same surface that we had, y equals x squared, but we're projecting it down onto the yz plane. So what we can do here is think about this surface. So that parabola is, what do we have here? It's it's y equals, this is y equals x squared. That's what that surface is. So if we graph that, we get that. But here's the thing. It's sort of being chopped off by this other surface. That's sort of what's chopping it off. That seems to be the actual cutoff here. Because if we look above the, excuse me, the YZ plane, it really does seem to be that this is the top surface. So if we sort of forget about this one for a second, we can just erase that. It really seems to be that this region here is bounded above by this. So what we can do is in our YZ plane, we'll graph 1 minus z equals 1 minus y squared. Now remember that the y-axis is really just z equals 0, and that's our other bounding thing. So it looks like, if we think about this in perspective, we really only want this portion right here. We don't want this left half, just the right half. So this region here, we want to do it in the order dz dy. So that means we want to say y is between two constants. So y is between 0 and 1. And then the z's are between z equals 0 and z equals 1 minus y squared. So our projective region, d sub yz, is equal to, or not equal to, but can be described by saying y is between 0 and 1, and z is between 0 and 1 minus y squared. And that right there actually gives us our bounds. So 0 to 1, integral 0 to 1 minus y squared, integral negative root y to positive root y, dx, dz, dy. All right, now that we're in the order of dy, dz, dx, the last order to do here, at least, yep, dy, dz, dx, I went ahead and I have created a line, parameterized a line that now extends only in the y direction. So the x and z coordinates are fixed on this line, only the y varies. So as you can see, we can go ahead and vary the a and c coefficients. We can move this up and down in the z direction. That takes it in our region. We can also move it left to right in the or in the x direction. So you can see that this line, let's move this down a little bit more in the more of the heart of our region. If we look at this, we always want to think about, so the positive y-axis you can now see is this way, coming to the left, and back this way is in the negative y direction. So this surface, which is z equals 1 minus y squared, that would be our top surface. And then our rear or bottom surface would be this surface right here. You can take a look at that. It's coming out the back. All right, so right now, let's go ahead and just write that down. So it looks like our top surface, or let's do bottom first. So our bottom surface is the parabolic cylinder y equals x squared, and our top is our surface z equals 1 minus y squared. So because we are doing this with respect to y first, that means our inequality that we're trying to build here is y sandwiched between two things, and these two things, whatever we put here and here, they have to be solved for y. So the bottom surface is already solved for y, so we can directly just import that without any alterations. So this is just x squared. Now, however, when we solve this for y, we're going to get a square root. So we're going to have a plus or minus, and we're going to have plus or minus the square root of 1 minus z squared. Okay, so which one do we pick? Well, notice that this surface here, z equals 1 minus y squared, that we want this half. This half extends in the positive y direction, where this other half here extends in the negative y direction. So that immediately tells us we want the positive root. Don't always just take the positive root, because sometimes you might want the negative root. In this case, we do want this half. We want the half that goes in the positive y direction. So this means we're going to go ahead and select y equals positive root 1 minus z. All right. So now what we want to do, so what we know now is that we can write this as the double integral over d sub, I guess this will be xz, because we're doing a y integral first, and this will be the integral from x squared to the square root of 1 minus z, 1 dy dz dx. So now we want to take this region here, and we want to project it into the y equals 0, so the xz plane. So we have to think about what is bounding this region. Well, let's take a look at our surfaces here. Here's y equals x squared. That's not, you can see that it's not actually this arc here, because this goes above it. So let's take a look at this one, 1 minus y squared. It's not going to be exactly that thing either. So this one is a bit tricky to do here. All right, for this next part, this more difficult part, we want to somehow figure out what this upper bound curve is when we're viewing the region from above the xz plane where y equals 0. So what I urge us to do is notice that the remaining two differentials are x and z. So this means ultimately we want to say, okay, x is between two constants. Because remember that the outside integral has to have constants. So if you look at your region, we notice that x goes from -1 to 1. So that's still true even when we're viewing it from above the xz plane. So x will go from -1 to 1. When x is between -1 and 1, we want to think about now, if we're at some x value between those two values, what is the range for z then? Well, no matter what x value we were at between -1 and 1, it's clear from looking at it from this perspective that z has to begin at 0. So the issue really is, how high up do we go? Okay, so let's just say we're at some x value. Let's say, for purposes of visualization, let's just think about us being here at 0.5. So if we're at x equals 0.5, then let's view this a little bit in from a not directly above the xz plane. So when x is 0.5, then what is the y value? Because the y value determines how high up we go. If our y value is all the way over here at the very end of this region, then our z value range isn't that big. But if our x value is close to 0, then our y value is close to 0, and our range for y is all the way up here, very big. So our x value, it's fed into y, and then that y value is what determines the range for z here. Because really, the maximum height you can achieve is determined on this surface here. This surface, y equals x squared, how high does it go? That's determined by where it gets clipped by this surface, z equals 1 minus y squared. So, as a progression of events, we have some x value, and then that x value determines the y value on this parabola, y equals x squared. So imagine we've got some arbitrary point here, some x value x. Then on the parabola, this green surface facing us, the y value is given by x squared. So then the z value here is determined by this parabolic cylinder, z equals 1 minus y squared. Well, if we're on this green parabolic cylinder, we know that the y value is x squared. So that means the z value has to be 1 minus y squared, which is 1 minus x squared squared, which is 1 minus x to the 4th. And if we are viewing this from above the xz plane, then this means that we want to express that upper curve, the xz plane, let's say, its equation is y equals 0. So we take this y coordinate of our point and make it 0. So this means we have x, 0, 1 minus x to the 4th. And that should be this upper curve here. And we can check this by adding a function, z equals a function of x and y, We'll edit it to be 1 minus x to the fourth, and there we go. Perfectly encompassing that. So that is actually the upper bound surface that we're looking for in the xz plane. So this upper function is 1 minus x to the fourth. So our final integral becomes integral -1 to 1, integral 0 to 1 minus x to the fourth, integral x squared to positive root 1 minus z, dy, dz, dx. That is a tough one to do because of this last little bit here. The projection's is not perfectly obvious. But there you go, setting up a triple integral of a region 3 different ways. Hopefully this was helpful for you all. Sorry that it was a long and drawn out video, but to see it done well and thoroughly, I think this is the best way to see it.